We are now going to talk about what a computer is and how does it work. The basic purpose of this chapter is to give you an overview as to how a computer works. Now, why do we need to understand it? Is it from a technical point of view? Not as much actually, because we are using computers every day, and it's important for us to at least understand in principle how does it work. And more importantly, as an executive in a company involved many a time in buying decisions about computers, it is important that we understand what are the components that go behind it, how do they work, how do you select, what are the criteria for selecting various devices for a computer, how do you decide on a configuration, so on and so forth. So let's begin by defining what a computer is. Here's a simple definition. A computer is nothing but a device, an electronic device of course, which does processing of information, and it does it pretty fast. So you of course know that the benefit of having a computer in terms of its speed, in terms of its repeatability, in terms of its accuracy, so on and so forth. Of course there are jokes about it in terms of uh, garbage in, garbage out, etc. So input, process, output is exactly the model on which a computer works. In terms of its basic components, computers are viewed as consisting of two things. One is hardware, which essentially is the nuts and bolts of the computer, and two, software, which is essentially the programs that we write to make the computer more usable from an application point of view. Now, if you look at uh, the two sides of it, and there's a tremendous amount of components which are constantly evolving on the computer, both on the hardware side and the software side. But look at some of the common ones. Hardware consists of typically a processor, the read-only memory, the RAM, the clock which is associated with the processor, the secondary storage, the input-output devices, things like the screen and the keyboard and such things, power supply which is part of the computer, modem which helps us to communicate with the outside world, and a bus which interconnects all these devices together. That's the hardware components that we typically talk about. On the software side, you have two broad categories of software. One, system software, and two, application software. Generally, a common sense definition of these could be system software is software which you and I generally can't write. So you need technical people, and many a time the software is closely associated with the machine itself, and it's designed for that machine. On the other hand, application software is something which makes the machine more usable from the standpoint of various business applications, various applications in real life. So if you look at the components within each one of them, you have system software composed of the operating system, which is the most important one, which actually drives the computer, which monitors the computer. It's like a supervisory program which constantly remains in the computer. Second, a set of automation utilities which are available. So day-to-day tasks that we perform on a computer, such as for example zip and unzip files, for example. That's one simple example of the kind of utilities that we have. If you were to do it by way of writing a program, it would have been impossible, but somebody has written a program and it comes along with the operating system, and to that extent utilities are closely associated with the operating system itself. Language compilers is the other set. What makes a computer useful to us is the ability to write programs in a given language, and makes it much easier for us to operate it subsequently as lay users of the computer. Database management systems. Most data processing today, business processing, involves a lot of data, and storage and retrieval of data is important. What has evolved over the years is a set of tools called database management systems, which ensure security, concurrency of usage, and large-scale storage and retrieval of data. And those are what database softwares are. Things like Oracle, for example, you would have heard, is an example of a DBMS software. And then, of course, today's world is that of a networking world. Communications is important. When you connect to VSNL or MTNL, where you have a broadband connection, you are essentially trying to use a communication software which helps you to do that. Now, communication software is broadly considered under system software because you and I can't write communication software very easily. The second main category of softwares is the application software. And within that, again, there are a couple of subcategories which have evolved. One is what you call as custom-made software. For example, if I want an inventory system to be developed for my organization, if I need a sales system to be developed, which is precisely matching the requirements that I have, I tell a software guy what my needs are, and he designs it using a given programming language. On the other hand, packaged software is something which is like an off-the-shelf software. So somebody could have, based on his experience of various companies and industries, written a generalized software for billing, for example, or for, let's say, for example, in the context of an institute, let's say the student learning software. Now, if you have such a ready packaged software available, you can buy that software off the shelf and start using it. However, many a time this is fraught with risk, in the sense that the software features may not exactly match with the features and the processes within your company. So either your company should be willing to adapt to that package and the way it has been developed, or the software should then not be used at all because it doesn't fit into your requirements. Canned software is a slight variation of the packaged software. This is also shrink wrapped. It's available off the shelf, but like a can, you just open a can of beans, for example, and start eating out of it. So it's absolutely ready made. So softwares like word processors, spreadsheets are probably examples of what we call as canned software. They require very little training or hand holding. They require very little installation and commissioning aspects of it, and very easy to use. The last category which has evolved over the years is enterprise solutions. Earlier, many companies used to implement small software solutions in each area, in each department. So you would have, for example, a payroll software, you would have a billing software, you would have an inventory software. Companies soon realized that this approach, which is a fragmented approach, does not work. What you ideally need is a software which encompasses the end-to-end business process of the company, right from taking an order to its delivery and everything in between. Now, these are softwares which are massive softwares which encompass the entire company's working, and also enables you to plan your company's resources well, utilize them well, and get the best out of your company in terms of performance. These, for example, the ERPs of the world, the enterprise resource planning systems, are good examples of enterprise solutions. But there could be other enterprise solutions. For example, you have a enterprise portal. So you need an intranet, for example, in the company. If there are generalized portals available which you could buy and make use of, those could be examples of enterprise solutions. CRM is another example. So there are off-the-shelf CRM products, things like CBIL and what have you, which you could actually buy and implement for your organization. But because their impact is widespread, it is across the organization, therefore they are known as enterprise solutions. Looking inside the computer, you will see how the components are stacked, and you'll find, for example, there's a power supply on one side, there are secondary storage devices on the other side. The CPU and most of the important devices are all kept on what's known as a motherboard of the computer. There are other boards such as these graphic cards and the sound cards, which do their respective functions of either sound or processing of visual display on the screen. You also have a whole lot of expansion cards other than these, for example, depending on the kind of devices you wish to connect outside. So you have ports, and ports are connected at the back end with these expansion cards. You could, for example, here have modems connected and installed into the system. So you will find this is typically how a computer looks like from the inside. Increasingly now there's a tendency to put as many components as possible onto a single motherboard so that wiring can be minimum, therefore data transmission speeds can improve, and the overall performance of the computer improves dramatically. Also, from a maintenance angle, if you see, if something goes down, you just unplug the board and replace it with a new board, and your computer starts working again. So if you look at some of these companies like Dell, etc., why is it that a repair guy can come and very quickly repair your system? It's because they have these circuit boards which are ready-made, which can be just plugged and unplugged very easily. Some of the input devices, just to name, which we are already aware of: keyboard and mouse and touch screen and scanners and trackballs, etc. A whole host of them which we'll look at a little later. Let's talk about the main heart of the system, which is really the CPU or the brain of the system. The CPU is essentially today a microprocessor. It's a complete computer in itself, a chip which handles all functions of a computer in terms of processing, storage, in terms of logic, in terms of movement of data, and in terms of controlling other devices. So fundamentally it performs arithmetic, logic, and data movement. CPU is characterized by a couple of things, and like I said, as a buyer, what should I be aware of? So one of them is the word length. So we many a times talk about a 16-bit processor and a 32-bit processor. Essentially, it's the word length. How many bits of information can the processor process at one go? And it depends on the size of the register inside the CPU, which decides how much of information it can accept at the same time. So a 16-bit processor handles 16 bits at the same time. That's the implication of it. Instruction set. Now, taking from there, the instruction set is a set of instructions which the CPU can process. So, for example, a processor can do an add, a subtract, multiply. Each one of these are instructions which the CPU is capable of handling. And depending on what type of a CPU it is, for example, there are two broad categories of CPUs, something known as complex instruction set processors, whereby you have innumerable number of instructions which the processor can potentially do, and on the other hand you have those which are known as RISC or reduced instruction set processors, which are capable or they are designed for a certain set of instructions. So they're very specialized processors which can do a limited set of instructions. And the analogy here is, for example, there is English language which, let's say, has about 20,000 words in the dictionary, but if you ask me, I might be using not more than even 1,000 words. That's enough of a vocabulary for me to communicate quite effectively on a day-to-day basis. So also for many business processing requirements, which is like routine, you don't need so many complex instructions really. So why can't I design a CPU which has fewer instruction sets, but it does it efficiently and well? And because of the fewer instruction set, the CPU size goes down, the processing speed goes up, and the overall performance of the CPU improves. So these are two broad strategies of designing CPUs: complex instruction sets versus reduced instruction set. And these are two different approaches in CPUs. Clock speed is the other measure which we normally consider. For example, you look at a CPU when you buy, you say, can you have a 2 gigabits processor? Can you have a 3 gigabits processor? Gigabits is an indication of the clock speed, or the rate at which the palpitation happens in the heart. So the speed at which you have your knocking in the heart. Now, if that's the indicator, it indicates how much of speed that you can generate in all the processing that you do. Higher the speed of the clock, generally speaking, higher the speed of the processor. Last but not the least, CPUs are internally designed keeping in mind a certain architecture. Also, the computer itself has a notion of an architecture, whereby how do you connect these various discrete components, the schemata or the scheme to which you decides the performance. So it's not good enough to have a fast processor, a fast disk, a fast printer. It's also equally important to ensure that these speeds match. The way they are connected ensures that there is no sort of a traffic jam anywhere in between, and that improves your processing speed. That's the notion of the architecture of a computer. To take a trivial example of what a processor looks like, let's take a processor which has 2 bits. So each bit a binary digit. So a processor capable of handling 2 bits of information at the same time. Every bit can denote either a 0 or a 1. So potentially you have 4 combinations possible. For example, असं दाखवू शकतो का? चालेल. So you have combinations like 00, 01, 10 and 11, which indicate multiple things. For example, if I have 4 combinations in a 2-bit processor, which is 2 raised to 2, it implies that every cell in the memory can be addressed. And how many cells can be addressed? Only 4 memory cells can be directly addressed. Likewise, if I have an instruction set, how many instructions can the CPU handle? 4. So for example, I can have add or delete, multiply and move of data. So this processor is capable of handling 4 memory locations, is capable of handling 4 instructions or performing 4 instructions. Also, because it is capable of handling a 2-bit number at a time, suppose you have a large number to process like a 4-bit number, you can imagine that it takes 2 cycles, clock cycles, to read the data, process it and push it back, because it can handle only 2 at a time instead of 4. Now the implication is very clear. Therefore, in general, if you have a higher number of bits or the word length, the implication is you get better speeds, you can access more memory, and you can handle large amount of data at one go. So if you have a 16-bit processor, it can handle 16 bits simultaneously. Therefore, complex calculations can be done in a quick speed. Hence, processors you would see in terms of word length have evolved from being 8 bits in the good old days in the 80s to 16 bits in the late 80s to 32-bit in the 90s and to 64 bits that we see today. The second major component, as we saw, is the RAM. RAM is random access memory. Essentially, it's meant for storing data in transition. So data which is being read from the disk, for example, stored in the memory till the processor asks for it. When the processor has done the calculations and stored the intermediate results, you again need memory. When the final results are calculated, again you need memory. And when you are about to ship the data back to the printer, for example, you still need some space to store the memory temporarily, because the printer is a slow printer and you need to send data slowly to it. Now you need to buffer the data somewhere, and that's where RAM is involved. So RAM is essentially a place where all transient data is stored. It's also a place where the current programs which are active, which are being executed, are stored, because programs are big. One instruction is being executed at a time, but the rest of the 99 instructions are stored in the RAM, and they are fetched by the CPU from the RAM as and when they are required. So there is a pipeline of instructions which keep getting taken from the RAM to the CPU, executed, data from the memory being taken as and when required, intermediate results stored back into the memory as and when appropriate, and finished data again being stored back into the RAM. That's the purpose of the RAM. Also, interestingly, there are a lot of status information which needs to be stored in terms of what is the status of the program at this point. So for example, if instruction number 10 is being executed, the status has to be remembered somewhere, and the memory location is allocated to store this status information as well. RAM, however, has a limitation in the sense that it is volatile in nature. So the minute you switch off the machine, the contents of the RAM are lost, and that's what volatile means. The other major resident of the RAM is really the operating system. So the minute you switch on the machine, you boot up the system, so to speak. What comes up in the memory first is the operating system, and the operating system, part of it resides there, part of it remains on the disk, because operating systems are very large programs, so everything can't be loaded at the same time, but some part of it is always active. It's like a supervisor, it's like a monitor, constantly watching over what's happening. So the amount of space allocated to the RAM, in the RAM, for the operating system is one part of it which constantly remains till the time you switch off the machine. Generally speaking, more RAM implies more performance. And why? Because if you have larger memory, you could have more data stored in the RAM. Therefore, CPU gets access to information faster compared to reading from disk, for example. So what I would typically do is pre-read information and store it into the RAM and make it available readily to the CPU as and when it needs it. On the other hand, you'll find if you have a large program and a complex program, all the program cannot be loaded straight into memory, but if you had a large memory, you could probably load the entire program. So the reading time required from the disk goes down. And just compare for a moment, RAM works at nanosecond speeds. The disk or the printers work in millisecond speeds. So you'll see the difference in speed. So it's important that you minimize the reading or writing that you do on disks or on printers, and try and bring as much as possible into the memory, which tremendously improves your throughput, as you call it, or the speed of performance of the processor. The second type of memory that you have is ROM. ROM is something which is pre-built, usually a set of instructions which are hard-coded and converted into an electronic form. So the minute you power up that ROM, the programs inside it get activated, the instructions get activated. Now, where do you use it? So, for example, all the basic knowledge that the CPU has, or the processor has, or the computer has, in terms of accessing disks, accessing printers, for example, all the input output, as you call it, the basic ability comes pre-built in the ROM itself. So the minute you boot up a system, power it on, the first thing that happens is a bootstrap loader, and all these ready instructions in the ROM get loaded into memory and get activated. The bootstrap loader in turn loads the operating system, and then the operating system is handed over the charge once the system is ready to use. So ROM is a very important component, but something which we can't disturb. It comes pre-loaded with the computer itself. The third type of memory, as we call it, is secondary storage. And why do we need it? As we said, RAM is volatile, and in business processing, or for that matter any kind of data processing, you need to be able to store and retrieve information over a long period of time. So therefore you need a mechanism to store information, and these are known as secondary storage devices. So all the data that has been processed in the RAM is finally sent to the hard disk for storage, for example. That's an example of a secondary storage device. So some of the other examples of storage devices include tapes, for instance, floppies, and now you use pen drives, and so many other devices which are all sort of secondary storage devices. What do you look for when you buy a secondary storage device like a disk, for instance? One is, of course, speed and latency. Speed implies the typically, for example, a disk rotates, and the rotation speed decides the speed at which you can access information on the disk. Because if you can imagine that there's a rotating disk on top of which there's a read-write head which moves around, the question is, if the disk is slow, it will take a long amount of time for the read-write head to come exactly at the point where your information is, and then read the information from there. So there are two components to the reading access time. One is the rotation speed of the disk till the point when the data comes just below the read-write, the actual time required to read it, and the time required to transfer it to the computer itself. So if these three components put together are known as the latency of the read-write mechanism, that's a very important factor in deciding the processing speed of your overall computer. So when you choose a hard disk with minimal latency. So for example, if I have a hard disk which rotates at 750 RPM, that's a typical speed which you get today, and then you have let's say a read-write access time of something like 20 milliseconds, that's an acceptable hard disk speed to look at. The other thing you look at is portability, because increasingly now you need smaller and smaller computers, so therefore you need small hard disks, but also you have sometimes external hard disks. For example, you connect directly to a port, and many times your machines don't have a hard disk, or you need a extra hard disk to take a backup of your existing hard disk. Now these are examples where portability becomes very important. So the form factor, as you call it, the size of the disk is very important, and as much data that you can pack in smallest area, that's the objective of the design of hard disks. We now talk about input-output devices, which is the next component on the hardware side, as we saw it earlier. Input output devices are devices which enable human communication with the machine. So either it is in the form of input which the human being is giving to the computer, or viewing output generated by the computer. So we've seen some of the examples of input devices, which are things like keyboards and mouse. On the other hand, you have typical output devices, things like monitors and printers. What do you look for when you buy input output devices? These are some of them. For example, you look at the character set. So for example, a keyboard has a certain type of characters which you can type. So some keyboards have 101 keys, some have 83 keys, some have 200 keys. Now all this means that you have a wide choice of characters which can be directly punched in from the keyboard. So character set decides the versatility of that input device in terms of how many different types of characters it's able to directly input. Some, for example, if you look at MICR, what you write on the check, for example, those MICR codes are written in a particular font and particular style, and only a few set of characters are allowed. So the character set is very narrow. In the good old days, for example, printers used to be only alphabetic printers. They would not even print numerics. Then came alphanumeric printers. Then they still didn't have graphics. Then you had alphanumeric and graphic printers. Now, of course, we don't think about it. Printers can print just about anything. So you have laser printers, for example, which print pictures in good quality. They can equally print text in good quality as well. But that's certainly an important design feature of a device. Resolution is the other thing. So while I can print or accept certain characters, what is the quality of that printing or that input that I take? That's known as resolution. So how reliably does the device represent the character which it is supposed to represent? So for example, many a time when you see these dot matrix printers in the output that comes, you have an A represented as a series of dots instead of a continuous line, because each pin on the head of the dot matrix printer pushes certain amount of ink, but that's not a continuous line, it's a series of dots. So that's low resolution for you. But if you wanted very high resolution, you needed a continuous line, which is what a laser printer today can do. That's the notion of resolution. Ports and interfaces. Now, all these devices, usually input output devices, typically a mouse, for example, a monitor, has to be connected to the main processor, and this is done by using ports and external bus connections. Now, there are standards to be followed, so I should not be in a situation where I have a device where I have a pin which does not go into my computer port. So standards, if they are practiced and followed by the manufacturers of these devices, then it becomes a plug and play, as you call it. And most input devices today, or output devices, are plug and play in that sense. Buffering and local storage. Think of a printer. So suppose you give a command to print a large document, and that document, of course, from the memory, it is quickly dumped onto the printer, but the printer has no local memory. It will print at its own speed because the printer speeds are ridiculously low. They are electromechanical devices, like we said. So can you not think about buffering the output sent by the computer, and if it can be done in the printer itself? So nowadays, most of these input output devices carry a local memory, and when you buy these printers, for example, you also ask the question, does it have local memory and how much does it have? So that the minute your printout is ready, the computer sends it to the printer, and the computer is free to do something else while the printer stores that data and keeps on printing at its own speed. And that's the benefit in terms of getting better processing throughput. Form factor is the other thing. Input output devices, again, because you need to carry them around, you want to transport a printer from here to there, you want to carry your monitor around, and if you have a small laptop, for example, the screen size is very important, because if you have a bigger screen size, the cost goes up, but also your weight goes up, and therefore you want a very portable device in that sense. Last but not the least, ease of use. So for example, sometimes when you look at devices like printers, they're very complex and cumbersome to use. So you're not able to understand them, you're not able to use them conveniently. If I want a reprint of the same document, can I do it? There's so many such features that you want. Nowadays, security is important, for example. So if I shoot a command for printing something and it goes to a shared printer where 5 people in my department are accessing it, I don't want them to see the output that is being automatically printed by my command. So what I do is I shoot a command from here, but I go there and at the printer I have to type a password. If I type the password, then only the printout comes. Now these kind of mechanisms are possible. These are value added features, make the system more usable. The last component is the bus. The bus is a sort of a data highway. It's a connector, it's an electrical connection, a wire so to speak, which connects all these discrete devices. So the CPU, the RAM, the storage devices, the input output devices, and they're all connected through a bus. So they pass information between themselves using the bus. But you can now imagine that therefore the bus can become a great bottleneck if that's the highway. So if everybody is trying to access it and trying to send information simultaneously, you need a fast enough bus to match the speeds of the CPU and the memory and the storage devices. So just to give an example of how bus can play a role in terms of enhancing the performance of your computer, here's an example of a simple architecture where there's a single bus and there are storage devices which, all the devices connected to the bus. On the other hand, there's another example of a similar architecture but with a slight difference. If you notice, the CPU has a direct connection to the RAM. There's a private bus which has been created. It's like a hotline. The CEO has a hotline. And why should I do it? Because if the CPU power is important and the CPU is like the CEO of the organization, I don't want to waste his time waiting for data to come from the data highway. Why can't I give him a private access to the RAM? Because the data he wants is in the RAM, the instructions that he wants is in the RAM, and therefore you create a direct memory access, as it's called in the last line, the DMA, which enables this direct access to the memory. Now suddenly you will find the processing speed goes up with the same components. This is the wonder of having a great architecture, and this is the role that bus can play in terms of enhancing the processing speed of a computer. Finally, ports. Ports are what you call as the external access points for connecting devices. We spoke about them with respect to input output devices, sometimes with external storage devices like external hard disks and such things, or pen drives for example. And the ports at the back end typically are connected to certain expansion controller cards which take the data from the bus and send it to the port and the device which is connected on the port, so on and so forth. What type of ports have we come across? Typically you would have heard about serial ports and parallel ports for example, and USB, which is very common now, and many devices in fact work on USB. Even printers today work on USB ports. So these are standards. So there was a serial port standard earlier, now there's a parallel port standard, and now there's a USB standard. By following these standards, like we discussed earlier, devices can become plug and play, and it makes it much easier for you to remove a device from one place and connect it somewhere else, and makes life more interoperable in that sense. One important component of a computer is, which makes it of course run, is the power supply itself. And while there is of course your external AC power which comes, you need in a computer, because this is a electronic device, it works on DC power, and therefore you need a converter, which is what the power supply does. However, computers actually have different components, the memory, the CPU, each one of them works on different voltages, and this power supply is designed to give you different types of voltage. So you have a 5 volt, you have a minus 5 volt, you have a 3 volt and a 1 volt, depending on what each device requires. The power supply is able to step up or step down that voltage in a DC format. Just to give an example of the kind of power that a typical PC draws, so it could be anything like 135 watts as mentioned here, or it could be 150 watts if you have more memory, more hard disk, say multiple hard disks in the same device, etc. then the power consumption goes up. So you can for a moment imagine that if you in one building, like in Wellinger, we have about 500 desktops constantly connected and they are switched on. So 500 computers constantly consuming about 135 watts of power. The amount of power consumption is huge. Therefore, nowadays you'll also find devices go into the sleep mode, and there's a setting inside the operating system which allows you to do that. So after X seconds, automatically it goes into sleep mode, therefore reducing the power consumption. From the communication standpoint, we have modems, and modems have, of course, an expansion slot inside. Some increasingly now you find inbuilt modems into systems, particularly in things like laptops. You don't have external modems that we connect. But modems are basically devices which convert digital format into a analog format suitable for a telephone line. So waveform, as you call it, or analog format is what it converts. Now, speed is expressed in terms of bandwidth, in terms of number of bits that you can transfer per second. And it's very common nowadays, for example, to have 56 kbps modems. And we need a lot of modems nowadays because we want to connect to 3G and such things, and broadband connections, etc. that we take. All in all, this is how a computer looks like. So if I am a buyer of a computer today, these are the components that I look for. These are the typical examples of or the configurations that I look for. I can ask for a Pentium processor or an AMD or a Core 2 Duo processor, for example, and I can ask for a choice of operating system, which is typically either a Linux or a Windows, and within Windows again, which version of Windows that I want. So there's the old Windows 98, but there's Windows 2000 and 2007, etc., which is now available. And then the size of the memory that you want. So that's something which you can decide. You now talk typically about gigabits of memory. So it's not even megabytes, it's gigabytes of memory. So you talk about 1 GB or 2 GB, which is standard in most configurations now. You have hard disks, which again could be of various types. You have read-write mechanisms. So for example, I have a possibility of reading and writing CDs, so those devices could be bought. You could have a variety of options in terms of screens that you buy, in terms of the resolution, in terms of the technology is used. Is it a flat one or is it a CRT based, etc. You have choice of batteries, particularly in laptops, and then you have types of ports that you want. And increasingly now the recommendation is, for example, you want to connect multiple devices like a keyboard, a mouse, you have one or two external additional devices like a printer, then it's a good idea to have multiple USB ports available. So you might ask for 4 USB ports, for example, in the computer that you buy. If you need voice output, of course, it's important to also look for speakers which are either built-in or separately connectable on the computer, and to back it up, a sound card. That's about the hardware side of it. Now let's talk about software and the kind of software which I've already touched upon, but in a little more detail. So for example, on the system software side, we discussed about utilities. I gave you examples of say WinZip, for example. You may have other utilities like for example, many a time the disk gets fragmented after long usage. So there are programs which enable you to defragment a disk, so clean up the disk, so to speak. Or there can be antivirus software, for example. So a lot of these could be more of general purpose utilities which you buy along with the operating system. Or FTP, for example, you would have heard of a software called FTP which enables you to upload data onto a website and such things, or a web server. Language compilers is the other thing which we discussed. So there are, I think last count, something 100 plus languages exist in the world, and each one of them requires a converter. So if you write a language in English-like notations, there has to be a software to convert it into a machine code which is then workable onto the processor. Database management systems are by and large meant for ensuring that you store data safely, you access and retrieve efficiently, and you can interconnect data and generate more holistic reports based on the data that you have. Security related software, networking and communication software is the other variety. Now increasingly you'll find many companies have very large IT setups. I gave you the example of Wellinger with 500 desktops. We have 1,000 students with laptops using it. You have almost 30 servers working in Wellinger. Now how do you manage all of this? How do you know that something is not working properly or something is probably malfunctioning? So you need softwares which enable you to monitor various aspects of your infrastructure in terms of utilizing your internet bandwidth, who's doing what. You also need, for example, from a security standpoint, what kind of websites are my students accessing, and I get log reports from the servers. Now all this is managed by infrastructure management softwares, which are becoming increasingly important to manage complex systems. And of course there are another wide variety of softwares that are available on the system side. We've discussed about the application softwares in terms of the canned and the packaged and the enterprise solutions and the custom made softwares using specific languages. So with that we come to the end of chapter 1, which is basics about a computer. So thank you for being with us.